Have you ever watched a drone just hang in the air, perfectly still? It seems to defy gravity, floating in place like magic. How does it do that? If you toss a piece of paper into the air, it flutters around uncontrollably. So what makes a drone different? The secret isn't one single thing, but a team of smart components working together faster than you can blink. We see drones everywhere now. They capture stunning aerial videos for movies, soaring smoothly through the sky. Some companies are even testing them for delivering packages, which requires them to land gently and precisely. In every single one of these jobs, the most important skill a drone must have is stability. Without it, none of this would be possible. A shaky camera gives you a terrible video. An unstable racing drone will crash, and you certainly don't want your package dropped from the sky. First, there's the constant pull of gravity, always trying to drag the drone straight down to the ground. Then there's the wind. It doesn't just push the drone from one side. It comes in invisible, swirling pockets of air. These gusts can tilt the drone, push it sideways, or try to flip it completely upside down in an instant. Even the drone itself creates problems. As its motors spin, they create vibrations that shake the whole frame. To stay stable, the drone has to sense every tiny disturbance and react to it almost instantly. It's like trying to balance a pencil on the tip of your finger, but imagine doing it in the middle of a windstorm. The challenge is immense. The drone must constantly feel what's happening and then know exactly what to do to counteract it. These aren't just for lift. They're the drone's hands and feet, allowing it to push against the air in any direction it needs. To go up, all four propellers spin faster, creating more lift to overcome gravity. To go down, they all slow down together. But to stay stable, they have to work independently. To fight a tilt, the drone doesn't move its body. It changes the speed of its motors. Imagine the drone gets tilted to the right. To fix this, the motors on the right side will instantly spin faster. This pushes the right side up and lets the left side drop, leveling the drone out perfectly. The same idea works for tilting forward or backward. This constant adjustment of motor speed is the key. But how does the drone know it's tilted in the first place? And how does it know exactly how much to speed up or slow down each motor? It needs a brain, and it needs senses. At the heart of every drone is a small circuit board called the flight controller. This is the drone's brain. It's a tiny, powerful computer whose only job is to run the motors and keep the drone stable. But a brain is useless without senses. You can't balance with your eyes closed and your ears plugged. You need to feel your position. The IMU is the drone's sense of balance. It tells the flight controller exactly how the drone is moving and tilting in space. Think of it as the drone's inner ear. It feels every single twist, turn, and jolt. The IMU is actually two different kinds of sensors working together, an accelerometer and a gyroscope. Let's start with the gyroscope. Its job is to detect rotation. It knows whenever the drone starts to tilt or spin. Gyroscopes inside the drone work on a similar principle, but they are microscopic, etched onto a tiny silicon chip. These tiny gyros can detect even the slightest, fastest rotation in any direction, pitch, roll, or yaw. When a gust of wind starts to tilt the drone to the right, the gyroscope instantly senses this rotation. That's half the story. The gyroscope knows how fast the drone is turning, but it doesn't know which way is up. For that, it needs help. This is where the second sensor comes in, the accelerometer. It measures acceleration, including the constant acceleration from gravity. When the drone is perfectly level, the accelerometer feels the force of gravity pulling straight down. But if the drone tilts, the accelerometer feels gravity pulling from a slight angle. It uses this to figure out which way is down. The gyroscope is great for sensing fast movements, and the accelerometer is great for knowing the drone's long-term angle relative to the ground. The flight controller combines the information from both sensors to get a super accurate picture of what the drone is doing at all times. So now the brain knows exactly how it's being knocked off balance. The next step is to react. First, the IMU senses a tiny tilt, Let's say a gust of wind pushes the front of the drone down. Second, the flight controller thinks. It receives the data and calculates exactly how much faster the front motors need to spin to counteract the tilt. Third, the flight controller acts. It sends a command to the front two motors to increase their speed instantly. This entire loop, from sensing the tilt to correcting it, happens hundreds, even thousands of times every single second. This is why the drone appears to be perfectly still. In reality, it is in a state of constant, frantic, microscopic correction. It's constantly making tiny errors and then fixing them immediately. It's a controlled fall that never actually happens. Engineers and programmers fine-tune this feedback loop using something called a PID controller. If it reacts too slowly, the drone will drift. If it reacts too strongly, it will oscillate and shake. The tuning has to be just right. So the stability of a drone isn't magic. It's a beautiful symphony of fast motors, smart sensors, and rapid computer calculations. It's a perfect example of a cyber-physical system, where software is directly controlling a physical object in the real world. Stability often isn't about being rigid and unmoving. It's about being flexible, aware, and able to correct yourself instantly. The next time you see a drone hovering, remember the invisible storm it's fighting and the thousands of tiny decisions it makes every second just to stay perfectly still.